We're given a piece of DNA and asked to design a pair of PCR primers that are going to amplify a sequence within our target. The DNA that we've been shown here is a double-stranded section of DNA. Convention dictates that the upper strand that we are shown, and usually the only strand that we are shown, will run from the 5' to the 3' direction, which means that the complementary strand underneath must be running 3' to 5' here. Now, if I want to design a pair of PCR primers to amplify this section of DNA, I'm going to have this primer as my forward primer, and this primer must run in this direction 5' to 3', and my reverse primer will be running here, and it will be running 5' to 3' direction. Putting the 5' and the 3' is forcing the direction of these primers in the direction that's been shown. And obviously this is the direction these primers must run in. If my primers were facing outwards, I would never be synthesizing the product that's in between the two. Now, if this is my forward primer and it's running 5' to 3' in this direction, because this is 5' to 3', the strand of DNA that this primer will anneal to must be the complementary strand here, which is starting the 3' end. So if I highlight in blue which is going to be my primer binding site, that is my primer binding site there. And if that's my primer binding site, it follows that actually the sequence that we see up top here is my primer sequence. And this is its 5' end, and this is its 3' end, and it's running in this direction here. So my forward primer is straightforward. It's as easy as you see it here. You take the upper strand, sometimes it will be the only strand of DNA that you are shown, you orientate it 5' to 3', and the sequence is as you read it here. If this is the sequence, it's binding to the complementary strand, and these are the nucleotides that it will start to synthesize as it reads along the complementary strand here. The reverse primer is running in the opposite direction, 5' to 3'. Because of this, this means that the reverse primer will actually be binding to the upper strand in this case, because here's its 3' end here. So if I highlight again in blue the primer binding site for my reverse primer, this is my primer binding site. So it follows that my actual primer sequence is going to be the complement to that primer binding site. So it is the sequence here, 5' at this end, 3' here. My primer will be running in this direction. So we have designed two primers here. One primer will be binding to the lower strand and synthesizing the upper strand of DNA in this direction. My reverse primer will be binding to the upper strand and synthesizing the lower strand of DNA in this direction. My forward primer is straightforward, and my reverse primer is being reversed. The orientation is being forced to run in this direction, and it's complementing the opposite strand of DNA. In this example, as is often the case, we're only being shown one strand of the double-stranded molecule of DNA. And it's always the upper strand that is shown, which means that it will be running 5' to 3' in this direction here. So if I was wanting to design another pair of primers to amplify a piece of DNA in this section here, I can imagine that my DNA binding site actually has to be the complementary strand of DNA that is running here, that we have not been shown. And if this is my binding site, my forward primer is the sequence that I'm shown here. The forward primer is straightforward. This is its 5' end, and this is its 3' end, and that is going to amplify DNA in this direction, synthesize DNA in this direction. This is the primer sequence, and this blue unshown strand of DNA is its target that it will be annealing to. My reverse primer has to anneal onto the opposite strand of DNA. So for the reverse primer, I'm going to highlight the primer binding site. Now the primer binding site in this case is the sequence that we can see, which means that my primer will actually be the reverse of the primer that we can see here, the reverse and the complement of it. So my C becomes G, A becomes T, T, A, G, C, G, C, all the way along. So that my reverse primer becomes this sequence here. So my reverse primer runs in this direction, 5' to 3', and it is the reverse complement of the given sequence of DNA that we could see. So if we have a single strand of DNA, the forward primer is straightforward, and the reverse primer is the reverse complement of the sequence that we can see. Let's look at one more example of doing just the same on another single-stranded section of DNA. So we're presented again with another sequence of DNA, and we've only been shown the upper strand of a double-stranded section of DNA. And again, we're looking to design a pair of primers, each primer being about 20 nucleotides in length. I know that my forward primer must be up here and running in this direction, 5' to 3', and my forward primer is straightforward. This section here will be the sequence of my forward primer. So my forward primer is 5', C, G, G, C, G, A, triple C, G, C, C, G, C, 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 G, C, G, G, 3' end here. That is straightforward. And my reverse primer must be synthesizing DNA in this direction, 5' to 3', and my reverse primer is the reverse complement of the section of DNA that I can see here. So my reverse primer, 5', will be reading the reverse complement from this end, C, C, A, G, G, T, C, G, C, G, T, G, G, C, 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 G, G, C, 3'. So after we had chosen a tentative pair of primers to amplify a section of DNA, we would then have to make sure that those primers were abiding by the rules for primer design. We would first of all have to make sure that our primer size was in the right region of about 18 to 24 nucleotides. If it's too shorter than that, our primer would start to lack specificity. And if the primer was much longer than this size here, the annealing efficiency would become reduced. We would also have to consider the GC content of our primer, which we would want to be in the region of 50 to 60% GC. I don't want long runs of GCs, and the GC here will affect our TM of the primers as well, our melting temperature. And we want the TM of the primer pair to be within 5 degrees of each other. Because if the TM of the two primers is too divergent, greater than a 5-degree difference between them, we can't use those primers simultaneously in a PCR reaction. Another consideration of the melting temperature of the primers, the TM, ideally for maximum PCR reactions would be within the range of 55 to 65 degrees centigrade. Furthermore, at the 3' end of the primers, we want a G or a C. This is called the GC clamp, and it just stabilises the base pairing at the 3' end of where the primer is annealing to the target sequence of DNA, which is necessary for efficient synthesis. And the last thing to consider is primer self-complementarity, where regions of DNA within the primer will self-complement. If a primer complements within itself, we get the formation of hairpin loops. And if the primer complements with the opposite primer, say the forward primer was to complement with the reverse primer, we would get the formation of primer dimers. And for either of these to occur on our primers means that the primers are inactive and wouldn't be available for the PCR reaction to occur, and it would severely limit the PCR reaction. So if I was to apply these rules to the primers that I have previously designed and found that some of my primers were lacking in any of these points, I would have to go back to the drawing board and pick another 20 nucleotides and start all over again and keep going until I found a pair of primers that applied to all these rules.